Now we're going to talk about finding flux, the flux across a simple and closed plane curve. Now we need to talk about what we mean by simple and closed. Here we see a simple curve. The definition of simple means that a curve does not cross over itself. So you also see this next curve I've drawn here, and this guy is not simple because we have this loop, and I really shouldn't say loop because we're going to use loop differently in a second, but it crosses over itself. What does closed mean? A closed curve is something that is actually, in a sense, a loop. It comes back around and touches itself. So it needs to be closed and simple. So a closed curve that is not simple may look like this. So this is a closed curve because it's a continuous loop, but it is not simple because it crosses over itself. It's important that we be able to distinguish the difference and understand that in order to calculate flux, we need a closed, simple curve. Now, what is flux? Flux is the action or the process of flowing in and flowing out. In physics, for example, it could represent the total electric or magnetic field potentially passing through a surface, or maybe even the rate of flow for a fluid, or some radiant energy or particles across a given area. Flux is actually Latin for flow, but many flux calculations, they involve no motion at all. So when our when we're dealing with a force field, and when that is an electric or a magnetic field, for instance, these are situations where we would be wanting to calculate flux. Now, the flux across some curve C, we're going to be calculating the line integral, but the definition is just a little bit different than what you may have seen or what we have seen in this lecture series before. So the first definition we're going to provide, if we have C being a smooth, simple, closed curve, which is in the domain of our continuous vector field, F. F defined as mi plus nj, which is in the plane. So n is a vector. It is our outward pointing unit normal vector on C. Then we can calculate the flux of F across C using the line integral of F dotted with that outward pointing normal unit vector. Now, this formula does not account for direction because a key part of this definition is that this n vector needs to be pointing outward. And depending on the direction which you traverse or travel along your path C, that n vector could point inside your closed simple loop versus pointing outward. We need it to be pointing outward. Now, the definition we just stated uses the unit normal vector n. N can be formed by T cross K or K cross T, but depending on the order in which you traverse that path, or the direction, I should say, I really should say direction. So depending on a clockwise versus a counterclockwise motion, you'll notice that we have K cross T pointing outward if we are going in a clockwise motion versus T cross K points outward in a counterclockwise motion. So if I had calculated for this second figure K cross T, then I would get these n vectors all pointing in, and we don't want them pointing in, we want them pointing out. So there's a further derivation. They talk about this more in your text. But since we want to define t cross n to equal n, and we want it to be pointing outwards, we need to use a counterclockwise motion. All right, so again, I've mentioned this before. We've talked about direction. We're going to start to see a little symbol that indicates that we must be traveling in counterclockwise motion. So here we have our new definition for calculating the flux of that force or force field across some curve or along some path C. And you notice I have this ring, this circle on my integral symbol. So this is a directed circle, and you notice there's a little teeny arrow on it that's pointing in the counterclockwise direction. So the way this is derived, the way we traditionally derive this, since there are two ways to calculate that n vector, is using a counterclockwise motion. Therefore, we have this little symbol or this little tag on that integral that says, hey, we must be going counterclockwise. And essentially all we're going to do, that's the integral, the line integral in the counterclockwise motion, we will use m and n in that integral, and then dy and dx. So we have m times the derivative of y with respect to t and the derivative of x with respect to t. And so these are both coming from my parametrized smooth curve R. And of course we have our bounds, t is between a and b. So again, we have our definition for calculating the flux of this force field across some path, C, as long as it's a smooth, closed plane curve. And the main takeaway from this is now we just can add this little ring with a directed direction. So it's saying we're calculating the integral, but we are definitely moving in the counterclockwise direction when we do this. So we have that new notation. Let's look at an example. In this example, we're going to find the flux of the field F across the circle parametrized by R of t equals a cosine ti plus a sine t j. A is just a scalar constant, saying that this could be a unit circle, but of any radius. So it doesn't have to just be radius 1. We could have a circle radius 3 or 5, any arbitrary positive constant number. Okay, so by definition, flux is the path integral in a counterclockwise direction along that path C, line integral, of m dy minus n dx. So paying attention to your order, it's not m dx, it's m dy, and we have a minus in there, n dx. All right, so let's find each of my components. I see what m and n are, but of course I want them in terms of t. So m is going to be 2 times x. X is a cosine t. N is x minus y, or a cosine t minus a sine t. So now, of course, I need dy, which is the derivative of a sine t, which will give me my dy value to equal a cosine t. And then my dx value, the derivative of a cosine t dx, is negative a sine t. So take a minute, make sure you can set up this integral. I'm going to pause and do that myself, but our flux integral is going to go from 0 to 2 pi of m times dy minus n times dx. Here I have my integral set up, m times dy minus n times dx. You guys should all feel comfortable calculating, simplifying an integral that looks like this at this point. Again, encourage you to pause, make sure you can work this out. Multiplying these together, I've got 2a squared cosine squared t. Distributing that negative and the negative a sine t, I get a squared sine t cosine t. Two negatives make a positive, one more negative, we have minus a squared sine squared t. To integrate these three terms, the first term we would reduce with one of those double angle identities. We'll say 1/2 times the quantity 1 plus cosine of 2 theta. For sine squared, we'll use a similar identity, 1/2 times the quantity 1 minus cosine 2 theta. And this middle term, we will use a substitution. Now I was being lazy up here and realized I hadn't written my dt, so it's dt of all of this. I can separate that into three integrals. Again, we'll use a double angle substitution for the first and third, and the center one we use a u substitution. Since all of my terms have an a squared, I factored that out. This is again 1/2, 1 plus cosine 2t, the 1/2 and the 2 canceled that. Here we can let u equal sine of t, then du is cosine t dt. So we'll just integrate that with the power rule and the substitution here. That's going to give us the 1/2 in front, and then we have 1 minus the cosine of 2t. So these are all very easy to integrate. Integrating 1, we get t. Cosine 2t is 1/2 sine 2t. Here, that's u squared over 2, so 1/2 sine squared t, minus the 1/2, which I'll still need to distribute. Integral of 1 is t, and again, the integral of cosine 2t, we're going to have 1/2 sine 2t, and that's a negative. Distributing that, we will have a plus 1/4. Combining like terms, t minus 1/2 t gives me positive 1/2 t. This 1/2 sine of 2t plus 1/4 sine of 2t gives me 3/4. And this should be a plus. We have plus 1/2 sine squared t. So good news is when I plug 2t into sine or 0 into sine, those are just going to zero out. So we're really just looking at a squared times 1/2 t from 2 pi to 0 gives us a value of pi a squared for my flux across that field along the path C. So there's our flux example. As always, email me if you have any comments, questions, or concerns, or you need help, because that's what I'm here for. Have a good day.